Thank you, Aisha, for the introduction. I spent my summer studying soil moisture observations from the Russian River Basin. On the screen is an example of how the Russian River is prone to flooding events during the winter time. As you can see, these floods can have devastating effects on the communities and the people that live along the river. Fortunately, there's a way to predict these events based on streamflow and soil moisture content. We can use something called the Sacramento Soil Moisture Accounting Model, we can use the SAC SMA to make predictions about soil moisture and the runoff. This model is part of a larger model framework called the HydroLab Research Distributed Hydrological Model. Since that's such a tongue twister for the rest of the presentation, I'm just going to refer to it as the model. So the National Weather Service uses this model to predict stream flow in the Russian River. Having an accurate representation of the true soil moisture field is important because the probability of flooding is highly dependent on how saturated the ground is. So, aside from flood forecasting, why else do we care about predicted soil moisture and stream flow? The Russian River is, at various points along the Russian River, there are inflatable dams that control how much water reaches different parts of the basin. These allocation decisions directly affect the agricultural communities, such as the vineyards and things like that, as well as certain endangered fish populations that rely on very specified stream flow levels to survive. Unfortunately, predicting these stream flow levels with computer models becomes a little more complicated in the winter because that's when they experience their regular their rain season. So we are currently researching ways that we can use soil moisture observations to improve the current prediction system. So here is a map of the soil moisture observing network that we use to extract our data. The red crosses indicate the 7 soil moisture probes that collect the soil moisture content at 15 centimeters every minute. The yellow line indicates the outline of the Russian River Basin. And because this basin stretches nearly 1,500 square miles, we're actually concerned that 7 soil observing stations wouldn't be enough to accurately represent how the soil moisture field behaves in time and space. So part of my project was to test whether or not this is a true concern. First, I'd like to show how we've used HMT data to compare to the model in the past. So when we look at the time series of the soil moisture observations and the model simulations, we see that differences exist between the two. In one past example on the screen, my mentor, Bob Zamora, he performed an intercomparison between the model and the observations, and he found that at one soil observing site, the electrical conductivity in the soil was throwing off the measurements. After applying a correction to that data, which was originally shown in blue, he was able to establish agreement between the model outputs, shown in red, and the new corrected observations that are shown in black. So this is just one example of how we can use the soil moisture observations to bring better agreement between the model and the observations. Another method that we're investigating to use is data assimilation. So before I explain what data assimilation is, I think it's first important for you guys to kind of understand how numerical weather predictions function. So imagine that today is Monday, and we want to predict something like the stream flow on Wednesday. For every grid on, or for every point on a weather grid, we can estimate initial conditions on Monday, plug those initial conditions into the model, and then get a simulation for Tuesday. To get Wednesday simulation, we can just plug Tuesday simulations back in, and poof, we've got a prediction from a few days from now. So what happens if the initial conditions that we established today are not completely accurate? As we continue to run the model through, we can see that these errors propagate through each simulation round, and by the end, the simulation on Wednesday is pretty far off from the actual nature of the soil moisture field. So this might be a good place to use data assimilation to improve on these simulations. So data assimilation uses soil moisture observations to update the model state and try to improve the simulations. This can only be done if the soil moisture observations that we use accurately represent the true soil moisture field. Also, these data need to be self-consistent in time. And finally, the actual difference between the model and the observations needs to be able to be minimized. So this is where I come in. If these assumptions aren't true about the data, then we cannot use data assimilation as a technique, and basically the work stops here. So we use 3 statistical tests to kind of check these assumptions. First, we plotted the autocorrelation functions for each station in the network to tell whether or not the data is self-consistent through time. So at each 6-hour lag period, we plotted the correlation between one soil moisture observation and all of the previous observations within that season. So we did this until we reached a point where there was 0 correlation left. And at this point, the data sets no longer have memory of themselves, and they can't be used to inform the model. So what we found is that in the summer and the fall, the data were self-consistent for around a month. That's actually not very surprising because in the summer and the fall, things are basically just drying down. There isn't any precipitation being added back into the soil to throw variation into these soil moisture observations. So that's why we see that the soil moisture field is evolving so slowly. Now, in the spring, there was a lot more variation in this data because of precipitation events and snowpack like melting and things like that. So we see that this autocorrelation period is a lot shorter. Still, in the worst case scenario, it was on about an order of 6 days, something like that. And you guys should remember that these observations are taken every 6 hours. So 6 hours compared to 6 days, it's still pretty good. Unfortunately, in the wintertime, our data was not stationary, so it kind of threw off, it invalidated this method to test for the temporal consistency in the data. So the second test that we did was calculate the correlation between actual observations at different points in the network. We did this to determine whether or not there are spatial patterns captured within the data. So what we found, again, in summer and fall, the correlation between each station they were very high. Perfect correlation would be 1, which is why you can see ones across the diagonal. It shows that each station is correlated with itself perfectly. But in both the summer and the fall, nothing dropped below 0.8, and that's again because things aren't really changing that much. What we were really interested in looking at is how things are correlated in space during the spring and the winter. We see that, in general, these correlations suffered quite a bit. But we were still pleased to see that certain stations that were close to each other in the network maintain that high correlation. So the spatial variations in the soil moisture can kind of be inferred between those stations. The third thing that we wanted to check is whether or not the difference between the model and the observations can be absolutely minimized. So what we did to do this, we took the model and the observation data and we found the difference between them. We then constructed a covariance matrix to see how the difference at one station and the difference at another station vary in time together. So we ran a positive definite test on this matrix, which basically tells us that these differences can be absolutely minimized. What's possible is that we could have a minimum between the observations and the model at between two stations, but not between another set of stations. So that could create an unstable point. And as I saw before, if you use unstable data to update the model, you can see that it can run wildly out of control very quickly. So the results of our positive definite test is yes, the difference between the model and the observations can be absolutely minimized. And I think that is the well, that's the main conclusion of our talk here. Because that difference can be absolutely minimized, it is now worth investigating data assimilation to improve the performance of soil moisture simulations. The other things that we found are that the data do reflect the actual soil moisture field spatially and temporally, although in the spring and winter, some of that suffers a bit. I think for the spatial to find spatial patterns better, we might want to introduce an actual spatial model based on the coordinates of the observing stations. But still, we will move on in the next steps of our research to investigate data assimilation. So yeah, I'd just like to acknowledge everybody who made this summer possible. I've learned a lot, and it's been an amazing experience, so thank you guys for that. If you guys have any questions.
All right, any questions for Enrique?
I was wondering, when you showed the numbers for the spring and fall that didn't really have great coefficients, that didn't correlate very well, or yeah, the spring and winter, I'm sorry. Could you come up with some certain distance measurement that would, like there would be a certain distance between stations that would be okay, and say if you go through that in the model?
You could. I haven't done that. But yes, that would actually be a step that we would use to kind of, I kind of mentioned using a spatial model to better interpret the spatial patterns in the data. That's something that we would have to do is kind of determine like a cutoff limit. You know, how far is too far away for these things to be correlated? I don't have a great sense of how far away these stations were. Oh, you have anything to say about that? I don't know. 49 square kilometers. So that's very good. Yeah.
All right. I had a question. Basically, in what proximity are you for your data sample to civilization or wells, and if that's put into your into the model, is it statistically relevant, or does that affect your data at all, or did you see anything like that?
I've never personally been to any of the sites. They've been running consistently since before 2011. But I imagine that a lot of them do exist within close proximity of civilization. How that affects the data, I'm not entirely sure. Again, I'm sorry. I haven't participated in a lot of the steps, in that intercomparison between the model and the observations. But a lot of what he does is try to assess things that are knocking the measurements or the model out of balance. So maybe you talk to him later and ask. I don't specifically know. I'm sorry.
I have another quick question. If that's it. All right. Do you know the depth of which your soil moisture essentially points were?
15 centimeters.
Oh, 15 centimeters. So not really affecting the phreatic zone and not getting near the water table, I'm assuming?
No, not getting near the water table. Phreatic zone, I'm not a hydrologist, so, but no, not near the water table.
All right, thanks.
Mm-hmm.
All right. Thanks, Enrique.